Chapter 5, Forces and Motion 1. We have two chapters on force. It is such an important concept in physics. We give the introductory concepts in chapter 5, and then we'll continue looking at problems with more facets and more forces in the problems and just more challenging problems in chapter 6. All right. I have a little cartoon here, and basically it's got this elephant, and if you've ever been around an elephant, this picture is even a little deceiving. They are an enormous animal, normally could easily push any puny little donkey out of the way. However, we are going to see in this chapter that if the elephant is standing on a frictionless surface, no friction, right? So if it's a frictionless surface, then it would be impossible for that elephant to be able to push the donkey backwards. In this case, it's really going to be like the elephant is just pushing himself off of a wall, and he will definitely go backwards, because if you were standing on ice and you pushed off the side wall, you would go backwards. So we'll talk more about that in another couple pages of notes, but again, physics, I hope, shows you that the world is maybe not as intuitive as we might at first see in all cases. All right, our first lesson is going to be on looking at inertia, mass, force, and acceleration. The first thing we're going to look at is inertia and mass, and the reason I circle them together here and that they're here together is that inertia and mass refer to the same concept. The concept is inertia, and mass is the numerical quantity we give to that concept. I know. Mass is something you've learned about, as a younger student, elementary, middle school, that mass is the stuff that makes up objects. So, it's a big object that has lots of mass. That's a small object that doesn't have much mass. Well, depending on the density of that object, the small object can actually have more mass than the larger object. And we're going to see that this concept of inertia is an inherent property of matter, and what it refers to is the property of matter that describes how much resistance to change for the object, to change in motion of the object, objects have. And the mass value we give quantifies that. So, if you look at our example here, the numerical example I have shown, I have an 8 kilogram object and a 4 kilogram object, and we're familiar with those types of measurements from science class in the past. So the 8 kilogram object obviously is twice the mass, and now we're going to say twice the inertia. So we constantly want to link the word inertia with mass. Twice the mass, twice the inertia. So if I want to push on both of them, so I'm going to give them both a push to the right, and I want them both to have an acceleration of 16 meters per second squared. We will see that you have to push twice as hard on the 8 kilogram mass because it has twice the inertia, twice the resistance to changing its state of motion. Okay, let me clean this up a little bit. All right. Let's see what else. Mass is definitely a scalar quantity. When you were in chemistry class, you never weighed out something and said, that's 3 grams north, right? That's just silly. You would never put direction with a kilogram measurement. The symbol for mass is m, so that's the variable that we are going to use. The units for mass are kilograms in physics. Chemistry, you probably have realized you used grams. And believe it or not, the English unit for mass is the slug. And No one ever uses slugs. I've never seen any use of the word slug, so if you find one, you can let me know. I would be interested to know what industry or scientists would use that. I do not know of any. All right. So now we're going to introduce the concept of force. And even in graduate level textbooks that begin to talk about forces for physics students, you will see the language that a force is a push or pull. That's the best we can do with language without using numbers and equations, okay? It's a force. A force is a push or pull. And look, notice it's the thing in quotes that causes accelerations. And this is because of this statement here. Force is actually a very abstract concept fundamentally. Now, in our practical use of it, we're going to see that pounds are force. So, you exert a force of 10 pounds, 20 pounds. We certainly can visualize it, but fundamentally, it is a very abstract concept. So, what we will talk about with forces will be the accelerations that they cause, not the force themselves. For example, when you think of gravity, like there's a force due to gravity acting on me, pulling down. Well, if I dropped an object, so I had a ball and just dropped it in front of you, and you watched the ball fall, and I said, well, what force is pulling the ball down? You would say, well, that's the force of gravity pulling the ball down. And then if I were to ask you, well, so you're observing the force due to gravity, if you think about it, you'd have to say no. What I'm really observing is the acceleration of the ball. I'm deducing information about the force due to gravity, and I'm saying there's a force due to gravity, but I'm really observing the acceleration. It's the accelerations and the due tos that really identify the forces. So here we have a ball falling, and we would say that ball is accelerating due to the force of gravity. A baseball that gets hit by the batter, we would say the acceleration is on the baseball, so the baseball picks up speed, gets struck by the bat, and goes off into the field, and that acceleration on the baseball is due to the bat. So there's a force on the ball by the bat. These ons and bys are going to be very important. As we go through Newton's laws of motion in detail, we will always be looking ons and bys. You don't have forces to really talk about if you don't have ons and bys. And we'll say that when a car slams on its brakes, what is bringing that car to a stop? Well, we're going to say there's an acceleration. Technically, it's going to be a deceleration, but even decelerations are accelerations, just backwards, as we've seen from our one-dimensional motion. But there will be an acceleration, well, I should say on, not of, on the car due to friction. So, when you exert a push or a pull on an object, we are saying there's a force exerted on the object. Now, forces cannot be seen. This is that abstract part. They are only known by their effects. And there are two effects that forces definitely have. The first effect, and Newton will put these into equations and laws of motion for us in another page or two of notes. But the first effect you see is that forces cause accelerations. Forces absolutely will cause accelerations. And when you push or pull on something, it pushes or pulls back at you. But now I have something to think about here. So we have, but what happens when you push on an object and there is no acceleration? Okay, we said forces cause acceleration, but you can push on an object and it doesn't move. Here's just the clip art I had to work with at the time, so I know over the years students have asked me why I'm using such a scary monkey, but it is what it is. All right, so we have a car stuck in the mud. Here's the problem. The car is stuck in the mud, and a kind, helpful, but scary-looking monkey comes up and says, oh, stay in your car. I'll push you out. I'm a big, strong, scary monkey. I can do that. So the monkey begins to push the car. So there's a force on the car by the monkey, right? Well, the car doesn't move. If the car doesn't move, then we know there must be another force on the car keeping it from moving. So technically, and I left it out on purpose, it's not that forces cause accelerations, and we can add it in here now. It's net forces cause acceleration. So add the word net in there for me. Net forces cause accelerations. So we have to look at all the forces on a car or on any object. So here we have the car stuck in the mud. There's definitely a force on the car, right? And if it's not moving, well, there would have to be a balancing force, right? It's a tug of war, a backwards force on the car down here, a force on the car by the mud, and if the monkey is not exerting a larger force than the mud can exert, then the car doesn't move. So notice if the monkey is pushing with 20 newtons, and the force on the car by the mud has a maximum value of 50 newtons, you would have to get to 50 point something for the monkey to be able to push the car. Okay. We do have, we'll talk more about it, but you can see we have a little bit of a problem here, because if the 50 newtons were always present and you were pushing with 20 newtons, then the car would move backwards. So we know that the mud won't actually move the car backwards. So if 50 is the max value and the monkey is pushing with 20, the actual force on the car by the mud would be 20 newtons, even though the maximum available is 50, and we're going to talk more about that later. When you push on something, it pushes back at you. So as we were talking about the elephant on the frictionless surface, if the monkey were also on a frictionless surface, it could not push the car out of the mud, because then the monkey would just be pushing off of the car and going backwards. So Newton is going to show us that the ons and bys are perfectly reversed. That's for every action, there's an equal and opposite reaction. So if there's a force on the car by the monkey, Newton realized, and this was one of his great epiphanies on how the world works and how forces behave, that you will have to have a force on the monkey by the car. They are equal in magnitude and opposite in direction. So if you've had science classes in middle school and have heard that type of language, we are going to dive into that and really nail down specifically what that language means. I don't really want to go more into this discussion here. I've opened up a lot of new concepts that we're going to further talk about as we go through our unit on forces, but right now you can do your lesson 1 homework problems, and we will pick up with lesson 2.